Hi. In some of the recent videos I showed you how you can use Circuitverse to build a device for a 4-bit adder and a device for a 4-bit subtractor. So we now have two devices. And in this video I want to show you how we can combine these two devices into one integrated device where we can use 1 bit to switch between these two operations. And I also want to show you how you can use this 16 segment display so that you can build a nice demo where the user can see that, for example, right now this device is doing an addition, and if you flip this switch, it's now doing a subtraction. For building this combined device, I will use an element from Circuitverse that I haven't introduced so far, the so-called multiplexer. And I will just show you by example how this multiplexer works. But maybe we will do an assignment where you're asked to give us a more formal mathematical description in form of a Boolean function for that. I also want to use the opportunity to introduce the counterpart to the multiplexer, the demultiplexer. There is actually not an application in this video for this, but it kind of makes sense to introduce both of them. So now let's go to Circuitverse. So let's begin with the introduction of the multiplexer. That's this symbol here. And here you actually have 3 inputs. 2 of them are here on the left-hand side with these labels 0 and 1, and one here at the bottom. It's called the control signal. And you have 1 output. Now, in order to demonstrate what this thing is doing, let me first get some input devices and an output device. So basically you can think of this multiplexer as a kind of switch where you either hand through the signal that you have here connected with the input 0, and this will be then connected with the output, or you connect the input with label 1 with the output. And what actually gets through depends on the control signal. So let me show you that. And I will have to increase the bit width to make it clearer. So here, if I'm using a control bit equal to 0, then the wire from input 0 goes through the output. And you see that this is actually the case, and it doesn't matter how I change here the value, this is not connected. And if I switch this control bit to 1, actually this is the signal that goes through, and this is ignored. And it can be made clearer if I'm changing the bit width of this multiplexer to, let's say, 4. Then I first get an error. You see this here at the bottom, because now the bit width of the inputs on the left hand side and the output also need to have a bit width of 4. So let me also change that so that we get rid of this annoying error message. Now I can use here different bit patterns on the input side, and now you see I can select the bit pattern from above or below, like that. And that's basically it. What we will see later, you also can increase the bit width for the control signal. Let me just show you what that means. In this video I don't have an actual application for that, but it will be very useful. You see here this control signal size, and if I increase this to 2, then I have 2 exponent 2 input devices on the left hand side. And we will come back to an example later. Now let me continue with the demultiplexer. That's this symbol here. It's basically doing the same thing reverse. So for demonstrating this, I also need a bit for the control signal. I also can use here a bit width of 4. Then I need an input with 4 bits and 2 outputs with 4 bits. And now I can delegate this bit pattern here from the input side to either the output device connected at the output with label 0 or to the output with label 1. I can switch between that like that with the control bit. Now, how can we use that for combining the adder and the subtractor? We begin with a adder. And then I need 4-bit input devices for A and B. And I need a 4-bit output device for showing the result. And I also want to have an output bit for indicating the overflow. Probably I need here a bit more space. And then I could now just connect A. Well, actually, I could give this a label. So this is supposed to be A, of course. This is supposed to be B. And I already can connect this. So for doing an addition, I just have to connect B with B, and that's basically it. Then I already could do the addition. If I also want to do a subtraction, then I have to choose whether I want to invert this bit pattern of B or not. And so that means I first of all need this NOT gate with a 4-bit width, and here we go. And now I do the following. I connect the input pattern with this NOT gate, and this gets into a multiplexer where I also need a bit width of 4. And this negated bit pattern gets connected here with input 1, and the original bit pattern gets connected with 0. And now I can use 1 bit to choose whether I want to have this inverted bit pattern going into the adder or the not inverted. And you see when I'm choosing 0, I'm doing the addition, and otherwise I would do a subtraction. But then I need here also a 1, and of course I can use the same bit here. Now you see, if I'm switching here to 1, I'm switching to subtraction. Now the adder gets the inverted bit pattern because we have this connection here, and it also gets a Cin equal to 1. So kind of easy. The only thing left to do is getting the correct indication for an overflow, depending also on whether we have an addition and subtraction. We have to either use this bit Cout as it is or invert it, and that means we need another NOT gate, and either we use the signal as it is or we use this inverted Cout. So actually I need here even more space. Okay. And then we need another multiplexer. And that's it. Now we see, for example, here we do not have an overflow when we subtract B from A, and we also don't have an overflow when we add these 2-bit patterns. We now do have an overflow, and now we don't. So of course now it would be nice to have this 16 hex display so that we can better show the user how to interpret the computation done by our device. Using the typical hex displays still is useful for showing the operands and the result. So this is supposed to be the result. This here is the bit pattern of A, and here it's important that we use the not negated bit pattern of B, the original bit pattern. And then, for example, see that here we somehow use 7 and 2 as operands, in this case for subtraction. Now, for understanding how this 16 segment display works, let me use this space here as a new playground, and I will connect this with a 16-bit input. And you see here above I actually made a sub-circuit for having a device where I just can easily can use it for later work. So if you connect the 16-bit input with this 16 segment display, you see with the single bits you can select which of these segments actually is on or off. And then you have to play around a bit which bits are necessary, for example, for showing the minus. And then we have here a mask, a 16-bit mask for displaying the minus sign. And then we could use a second input device with 16 bits. Play here around, we certainly need these two segments, and then we have to figure out what else needs to be set to 1 in order to get this plus sign. And now again we can choose, do we want to have this plus or this minus, and now I basically realized that I should have switched places here. So this should be 0, and then I can use another multiplexer. 16 bits here. Now I can select between 0 gives me a plus and 1 gives me a minus. Now if you change these 16-bit input devices into constant input devices and give this control bit label, for example like select, and the output instead of using here a display should be a 16-bit display, basically what I did here, then you can use this here as a building block like that, where I can choose here which sign I want to have, and then you see here in my demo I just use this. It generates me from this selector for the operation the right mask for showing the sign, and then you're done. So that's it for this video.